Welcome back. Today we're starting right where we left off in part 1. We've got our moving assembly, but one of you mentioned in the comments that we're cranking out some serious on-shape horsepower. Today we're going to prove it. We're moving beyond kinematics to see if our engine internals can actually handle the heat using Onshape's professional simulation tools. Before we start clicking, I want to consult our Onshape AI Advisor and ask him about how to set up a simulation. Here is the reply. Okay, first you need to assign materials to all parts. Then you need at least one fixed component. Okay, I'll keep that in mind. So now I want to illustrate in context design using our engine. First, I'll rotate the crankshaft to top dead center. Now I'll go to the command create part studio in context, show our mates, and pick this one. A part studio opens and I see our existing parts in transparent mode. I can adjust that according to what I like. And now I will start modeling. I'll take this plane, project some edges from our existing geometry. That's enough. Then take the rectangle tool, pressing Alt for a square, apply a dimension of 12, and exit that sketch. Go to the extrude, take these two regions here, and make an extrusion up to that end face. I will rename that housing. Change the appearance here. Then apply a chamfer. Pick one edge, make a right mouse button click, and so go to the select option and take the equal length. So all four edges are selected. I'll take the 48 value here. Next, I will shell, make a hollow part with a 8mm wall thickness. I'll hide all planes, make my next extrusion, show that sketch, pick that circle, remove that, going through all. I'll start the next sketch on the side of the housing, project that circle, go into the extrude, make a thin extrude off that circle with a 6mm thickness up to that face. I'll accept that. Go to the move face command, take that region, that face, and make it a blind extrude of 66. I do want to remove that face. Go to next. That's a solid remove. Okay, I will show this in section view. Take that one plane here for my section view. Okay, that extrude didn't work out, so I will pick that face again up to next, and that is what I wanted. I'll continue with a surface tool, fill, take that edge, there's our surface. I will thicken that, adding to our housing with a thickness of 6. And I can hide that sketch here. I'll model some cooling ribs on that face, projecting that edge and offsetting that one with 14 millimeters. Exit that sketch, extrude that with 12 millimeters going towards the housing. That meant to be adding to our housing. Now I will pattern that feature. Direction is this one. I'll reapply that feature and make that distance 24 times 12. Next, I want to pattern this part over to the other 4 pistons. So I'll go to the linear pattern of features. And let's see where we started here. That was the first, that one, that one. Take all those patterns here. Direction will be this one. Reapplying that feature again. And about that distance, remember that we had these variables, that interval. So this is what I'm going to insert here. Interval times 2. There is the second one of those. Now I'm going to mirror these features over this plane here. Accept that. Then, okay, we need to move these up, and we can do so again by the move face command. We'll just make a window select of these. Go to the translate. The direction is again this one. And just move that by 1 interval. All right, so that's it for modeling. And now we're ready to start our simulation. All these arrows indicate this context we created in the assembly. Context number 1. So I'll go ahead and insert our part in our assembly. I'll continue with the section view. And exclude these two parts of the section, because here is where I want to apply our simulation. I'll make this housing a fixed component, and before I forget, I will apply the materials to our parts. For the crankshaft, I'll apply steel 4130. This is a high toughness alloy. Let's have a look at the properties, especially the tensile yield strength. This is the most important one for our safety factor. That value in megapascals is 435. I'll apply the same material to our rod. This one. And for the piston, I'll take an aluminum, the aluminum 6061. Let's go back to our assembly. Now let's make that simulation. One thing to note, these native FEA tools are a professional feature. If you are on a student or free plan and don't see these options active, you can get a professional trial using the link I've put in the description below, so you can follow along. I'll pick this one, the force, apply that to that rod, the load direction will be in this axis. I'll turn that around and apply a value of 7,000 Newton. I see that here our simulation, and I'll go to show results. All calculation is done in the cloud, so it doesn't tax your computer. And there we have the results. Let's have a look at the displacement. And here's the value, 3.69. That's about 37 microns. To put that in perspective, that is less than half the thickness of a human hair. There's a deformation scale and a play button. Okay, that's a bit extreme. For my taste, I'll put that to 200. And so we can have a visualization of that displacement. Let's go to von Mises stress. So there we see the areas of the highest stress. We can pick the sign von Mises stress. There we have negative values and positive ones. Negative values indicate a compression, and positive values indicate a tension. This indicates that the material is being pulled or stretched. Sure, we can animate that as well. Let's have a look at the safety factor. And it stands at 3.5. The safety factor of 3.5 means that the engine could survive 3.5 times the current combustion pressure, up to 24,500 newtons, before the metal even begins to permanently deform. Let's have a look at the simulation panel, which you can find here. Here we have the control over our simulation and can find all relevant information about it. We can as well add a simulation. We have the choice between a linear static simulation like the one we got, or maybe a modal simulation. In case we have a doubt about what a modal simulation is, we'll just ask our AI advisor again. And we are informed that a modal analysis helps to identify a structure's natural frequencies and mode shapes. We can modify the forces of our loads, review the direction of that load, fine-tune the appearance, the color scheme to blue-red or plasma rainbow. I'll go back to varieties. There's an option to indicate minimum and maximum values of a selected result. So there would be the minimum in terms of safety factor and the maximum. One of the most powerful things here is how Onshape handles connectivity. Under the settings, you can choose how the software interprets the touch between parts. By default, it uses our assembly mates, which is incredibly efficient. However, you can also manage connectivity logic here. Mates and touching faces, or just mates, and bond all touching faces. This tells the solver exactly how force should flow from the piston face through the pin and into the rod. We'll stick with a mate-based connectivity today because our assembly is already fully defined. It's impressive to see how everything is integrated into one platform. Designing the parts, building and animating the assembly, simulating the physics, and even having an AI advisor on hand if you have any doubts. Integrated engineering, that's the Onshape difference. I thank you for tuning in.